So I think at the last time, at the end of the hour plus last time, we considered, okay, if I do work by raising, I'm so strong, work by raising up this, it's actually made out of, what's really heavy? Tungsten. Yeah, it's really heavy and, okay. So the force of gravity is down. If I'm going to just move it up without accelerating, it just moves up, then what can you tell me about the normal force on the chalk? Okay, if it's not accelerating and F equals ma and the only two forces on it are gravity and the normal force, then the normal force must be equal and opposite to gravity. So that normal force is a force against gravity. The work done by the normal force against gravity would be mg times the displacement y. Do you buy it? Right? We'll take that silence as consent. Okay, so one of the things about work, we have to be clear. Are we, was there a question? What, Jonas? I don't know. Okay. The work against the force, I have to do work against the force, and that gets stored, at least in the case of gravity, in the form of potential energy. What's another example? Well, we've considered this one. The work that I have to do in order to compress the spring is opposite to the work the spring does on me, because the forces are equal and opposite, and that work gets stored as potential energy, 1/2 kx squared in the spring. This is stuff that we have worried about before. These are familiar forces, so I now want to consider more generally. Well, in general, the force could depend on place, like gravity. It could depend on velocity. Have we seen an example of that? Yeah, drag force, very good. Could depend on time. How would that work? How would that work? I have no idea. Okay, so I could supply a force. You know, I could do that and have a time-dependent force. Okay, so those are hard. So I'm lining them out. Right? Yeah. What? They were there and they've been crossed out. Why? Because if we worry about, well, those are not going to turn out to have a potential readily definable. Or it's more complicated. So in the case of, I'm going to ignore the frictional bit and we can maybe come back to that. Okay. So the claim that I want to make to you, and I think we sort of discussed it a little bit, is if the work done in going from point A to point B in a force field, which sounds a little, what, Star Trek-y or something, I don't know. If it's independent of the path that you take to go between A and B, then we call the force conservative. So I have an example force field. It's beautiful. I have been growing it, you know, I watered it, and actually I didn't water it, it's just blue. It's deoxygenated. All right, so is that a conservative force field? Would the work done in moving from some random point A to some other random point B depend on the path or be independent of the path? I think we've argued this one, right? We said, look, that's a uniform force, and so it doesn't care. All it cares about is the net displacement. So on that one, how could I show that more formally? So to me, this looks like the force is some crummy constant in the negative y direction. So F is equal to K for crummy constant in the y direction. And the little bit of work done will be dW is equal to F dot ds. And then we're going to integrate that. So the work done in going from A to B. All right, so I now sub in my definition for F. Okay, that's minus some crummy constant times a unit vector in the y direction. How do I write ds? I mean, I haven't showed you the path. It could be some crazy-ass thing, right? I mean, so what in general would be ds? Could it change in x? Yeah. So it would be the little step in the x direction, but it could also have a little step in the y direction. And how much of each of those is going to depend on the path that I take in going from A to B? Well, okay, this is where the dot product is my friend, so it just kills that immediately. Because no matter what the displacement in x, the x unit vector is perpendicular to the y unit vector, and so the dot product is 0. And that leaves me then with an integral from A to B of what? Minus k dy. And so that is only going to care about how far did you move in the y direction. So it's independent of the actual path taken. So this would be minus k delta y, if you like, AB, where delta y AB means y at point B minus y at point A.